hello. Happy day.
I just realized that Mr. Bobby and I didn't even talk about matching today. I totally would have gone to put black on.
Well, actually, it's navy blue and it's a corgi. I don't think you have a corgi unicorn floating on a rainbow t-shirt.
I don't. It's sad. It's a sad,
No.
sad day.
Yeah.
So today we're talking 4.8 mean and standard deviation of random variables. So we kind of introduced random variables and we're kind of chatting about it. And so we want to do a couple of things today. We want to look at parameters of discrete random variables, and then we want to calculate and interpret them. When I say parameters, Mr. Bobby, what am I talking about?
You're talking about things that describe the distribution, I think. You're talking
generally
about
one number that describes. And I feel like I need to circle back to this. I just graded your FRQs for your Module 3 exam, and you guys did a wonderful job talking about the distribution, except for probably more than half of you are still talking about range as like the range is 23 to 62. Like, remember that range is one number and you subtract big minus small. Okay, so circle back to that thought in your head. Like, if you're going to use range to talk about variability.
And remember, you only use range with median. And when you start talking about mean, which we're going to be doing a lot more often, then you need to use standard deviation.
Right.
And that's what we're going to be talking about tonight.
Yep. Okay, so a numerical value, see, value 1, measuring a characteristic of a population or the distribution of a random variable is known as a parameter, which is a single fixed value. Just one.
And the first one that we're going to use very often is the mean. And when we talked about mean in middle school, we added up all the numbers and divided by the number of numbers. Well, mean can be a lot of different things, can mean some different things in different parts of statistics. And when we're talking about random variables, like when we were counting the number of heads that we get when we flip coins, it's the probability of that event happening times the value of that event added up for all of the different trials. And we're going to see that here in a little bit, but it essentially ends up being similar to what we did in middle school, but that formula looks worse than it actually is.
Right. So when we're talking about these discrete random variables, we tend to call them expected values rather than mean. And if you think about that, that makes sense. A mean is what we expect. It's what happens on average, right? So like when you're driving to school in the morning, you would expect to see 22 cars. Like on average, you're going to see 22 cars. So you would expect to see about 22 cars. So it's the same concept. It just makes a little more sense to say expected value in some contexts. And this is the ugly formula for it, mu of x. So that x, that sub x is standing for your discrete random variable. And we might call it E of x, or the expected value of x, which is the sum of all of the values times their probabilities, okay? So that's gonna make more sense in just a minute.
And like she said a minute ago, you might see 22 cars on average on your trip to school, but that would vary. If you saw 23 one day and 20 the next and 24 the next, there's some variation, and they'll vary on average by the standard deviation, or up to the standard deviation.
Right.
And we'll talk about that too in a minute. I think it'll be a little bit clearer once we actually do an exam.
Right.
So. And
then you've got the big ugly formula here. We're going to walk through that formula. AP exam doesn't really require you to use this formula, but they might ask you a multiple choice question about what would happen if you changed part of it. And so you kind of need to know which formula to look at to have an idea of how that would affect it. The other thing that I want
to... Always, last one, the best bullet point is our baby. Oh, sorry, we were going to say the same thing, weren't we?
Yes.
What were you going to say about that last bullet point?
No, you go. You were ready.
I had my finger pointing at you. My finger pointing at my webcam. You be specific. You talk about the problem, all right? We don't assume we know that what we're talking about, what you're talking about, just because you did a bunch of math.
Right.
Okay.
So always appropriate units, always context. And basically, don't give me a naked number. I don't want it.
Yeah, you need to tell me that number. And really, you're just going to parrot back the topic of the problem. It's the easiest points on the whole test.
Yes. Just don't forget to do it.
Just don't forget to do it because so many
You'll
people
be
do.
so proud, like, I got an answer. And then you'll forget to be specific. And the graders will be like, meh.
All right, so let's do it. All right,
Okay,
so here's
the
the
expected value is often referred to as the long-term average or the mean, long-term average. So remember me shooting 3 free throws, that long 100, 200, 1,000, right? That long-term average. So we call that expected value. This means that over the long term of doing an experiment, over and over, you would expect to see this average. So maybe not the first time, maybe not even the first 10 times, but maybe after 30 times.
Okay, so we have a problem here about men's soccer team that plays soccer, and apparently they're not really too heavily into soccer because they only play 1 day, 2 days, or I'm sorry, 0, 1, or 2 days. They don't play like a lot. It's probably us over 50 crowd soccer. You know, we go out there and call it a game, all right. But they're not really into it. But they play a little bit. Okay. Anyway, the probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5, and the probability that they play 2 days a week is 0.3. So we're going to try to find the
Yeah.
expected value or that.
And let me
mean.
clarify that just a little bit. So what this says is 20% of the time they don't play. They play 0 days a week. 50% of the time they're only going to play 1 day a week. And 30% of the time they're going to play 2 days a week. And we want to know, like, okay, that's interesting, but what do we expect to happen? Like, given a random week, right? Given a random week, how many times do we expect to see them out practicing? Because more often than not, or like, I guess 50-50 chance, they're going to be out there 1 day a week, right? So we're looking for, okay, what would we expect to see happen? So how are we going to do this, Mr. Bobby? Think about the formula.
That formula was the probability of that x value times, that was the x value times the probability of that x value. Okay. So what I'm going to do is I'm going to take the number of days they play times the probability they play on that day. So I would start by saying 0 times 0.2. That's the probability, the value, which was 0, a number of days they played was 0, times the probability that they play that many days a week. And then I'm going to add to that the others. So the value of 1, that occurs with 50% probability or 0.5 probability. And then finally, the probability that they play 2 days a week times its probability, which was 0.3. Okay, so it's day times probability plus day times probability plus day times probability. And then I got to do some math. Okay.
Gross.
Well, the first one's easy.
0.
Second one's easy.
0.5.
And the third one's not hard. It's 0.6. So now this is what's weird. 1.1. Okay. 1.1 what?
So, and I'm going to even back up from that. Can we have an expected value that's larger than 1? Because we've been talking this whole unit, stay between 0 and 1, stay between 0 and 1. Doesn't make sense if you're outside of 0 and 1. So what is expected value finding in this case? Go back to your X value, and this will help, okay? You're finding the expected you should be writing this. Yeah. The expected number of days played. So is it okay that I have a number bigger than 1?
Well, and is it okay that I have a number that has a decimal point? Because I can't have 1.1 something. And first of all right, so that's 1.1 days, right?
Yes.
This is what we're talking about with the units. Okay. So that's the number of days that we would expect them to play on average. So there's a famous, there's always this famous statement about the average family has 2.3 kids and a dog, or something like that. Well, how do you have zero point 0.3 of a kid? Well, that just means that many families, many families, there are more than 2 kids, and some families are small. So we would expect the soccer team to play on average 1.1 day per week. Okay. Now, granted, some weeks they're going to play more, some weeks they're going to play less. In fact, any one individual week would they actually play 1.1, but over the many weeks, it would average out to 1.1 days per week. Okay, long term, many, however you want to say it.
Many.
All right, many. We like
Okay.
many.
All the many.
All right, we ready to do some babies?
Yes, we need to clear the screen. Clear. All drawings. Got it. Look at this sad baby. You got him. Okay. It says find the expected number of times a newborn baby's crying wakes its mother after midnight. The expected value is the expected number of times per week a newborn baby's crying wakes its mother after midnight. Calculate the standard deviation of the variable as well. And we get this table of info. So you want to start us off here?
Yeah, so I wouldn't know anything about this because I don't have kids, but I'm sure Kedron probably woke you up at some point when she was a baby. But babies will do that. They'll cry, and mom or dad or both will have to go get them. And we have the probabilities in that first column. The probability that baby would never would wake their parent no times during the first week during a week would be 2 out of 50. And then the probability of 1 would be 11 out of 50, and so on. Okay, so we have those probabilities. And what we've done in the second column is taken the x value, if you notice the x value, times the probability. So we 0 times 0.2, 1 times 11 tenths, and so, or 11 50ths, and so on. And so what are we going to do to find the mean is we want to add these guys up. All right. So do you have that already on here, or is that on the next page?
I do have it on here.
You had it annotated on here the same. She added them up and got 105 over 50.
And guys, it's perfectly fine for you to leave it as 105 out of 50 on an open response question. Okay.
Yep.
If it's a multiple choice, they're gonna reduce it probably, or maybe not. Sometimes I've seen them not reduced, but you do need to be prepared for the fact that it could. Okay. And so what we would say is mu, and I should have said here, mu of x, or the expected value, is 105 out of 50.
Well, and I don't think we ever officially defined x. You got the table,
it's defined,
but is it defined in the problem?
Well, let's see.
I don't think you text your prompt.
Yeah.
I'll get it. And notice and this is the second time I've done this, you always want to, the problem may define the variable. If not, you need to define it, okay? Oh, well.
So many things. I don't know what just happened.
You're out of the slideshow.
I'm not out of the slideshow is what's crazy. Here, let me go back.
Yeah.
There. I wasn't out of the slideshow. It just brought my bars up at the top for some reason.
Yeah.
Not sure why. But let me bring the answers back.
Okay. So the number of wake ups is X. Okay. And again, you just want to spit back the topic of the problem. That's that context thing that we're never going to let go of that.
Yeah.
Okay.
So the next column, you have to recognize it. And this is what I was telling you, there's a really good chance you're never going to be expected to ask or to actually determine the standard deviation from scratch, okay? But like, if you're given this formula or this data, you should be able to recognize this as part of the standard deviation, okay? So it's taking each X value, subtracting the expected value, which 105 out of 50 is 2.1, okay? Subtracting the expected value, squaring it. This is our standard deviation from way back in module 1, okay? So now we're taking the traditional standard deviation formula and each time multiplying it times its specific P of X, okay? So 2 out of 50 is 0.04. So take a second. I'm being quiet because I'm hoping that you're kind of processing this because it's a lot of information.
Yep.
Okay.
So that's the probably for the first one, and then we're going to do 1, 2, 3, 4, and 5 as well in the same way. We're still going to take 1 and 2 and 3, subtract it from the mean, which we go is 2.1 times its specific probability. The 0.22 is 11 divided by 50, and we get a number.
Yeah.
And then we're going to add them all up.
So going back to the formula, the next step would be the summation. So at that point, we want to add all these up. So we get 1.05 in this case.
Thank you for doing that for me. I didn't want to do that.
Now, unlike the expected value, you're not done at this point, okay? Because this formula also has a square root attached to it. So this has one more step. You can't just stop at taking the sum. You have to take the square root of it, okay? And that is actually going to give you your standard deviation. And remember that sum, before you take the square root of it, is called the variance. Mr. Bobby wrote it for you. I put you a big arrow there. It is called the variance. So standard deviation and mean. This is what they look like. To find the mean, probability times expected value, add them all up. To find the standard deviation, follow that big, ugly, long formula. But really, it's more important. Expected value, you're probably going to be asked to find it by hand. Like, it's probably going to happen at least once on the AP test, okay? But standard deviation, no. But what you probably are going to be asked is, can you interpret them? Do you know what they mean, okay? So we're going to jump off of this slide, and we're going to hop over to this slide, and I'm going to give you, you pointing at us again?
I'm pointing. I'm what's the big finger in the webcam mean?
Be specific.
Specific. Talk about the context. We did all that work, and we got, and this is what is so frustrating to us as teachers. We know we've covered it. But you're doing the hard lifting, doing all that math and all that arithmetic, and thinking through all those formulas, and you've done it, and then you're like, forget to tell me what it is. Well, just tell me, what is this all about? Well, we're talking about, what's the topic of this problem? What was the topic about this problem again? I've already lost it. I don't even know anymore. I just know
babies crying.
Oh yeah, it's about crying. It's about babies crying. Okay. So, and what was X? Now we've erased that because it was in the previous slide, but we said X was the number of times the babies woke up the mother. So 2.1 is our standard deviation, right? So
I'm ready to type, Mr. Bobby. You tell me what to type.
So we would expect the expected number of times that a newborn baby would wake up the mother would be 2.1 days in a week over many, many weeks or something along those lines.
Now, what I'm doing right now, because I don't remember all those words he just said, is I'm literally typing this first sentence where it says find the expected value of. I'm just reiterating that. the expected number of times a newborn baby's crying
Just
wakes
wait. She is so smart right now. The easiest thing is literally spit back exactly what's in the problem and then throw your number after it.
is 2.1 times,
Yay. Yep. Okay.
right?
Yep. And that would work. If you just copy the text of the problem back in your conclusion, you're golden because they can't argue with what they told you. Okay. Now the standard deviation would be 1.0247, and that would be the standard deviation of and that's how many would vary. Remember we talked about the cars being 22 or maybe 24 or 20. They would vary. The standard deviation of the number of times a baby would wake up a parent would be 1.0247. You typing or
So
not?
we would say, what did you just tell me to type? I'm sorry.
The standard, the standard deviation for the number of times the baby would wake the mother is 2.0247.
Now, what I
This
just did
there
there
comes
is
me.
I did not interpret. Okay. So all I did there is state. So if the directions said interpret, I need to go a little deeper than just stating.
Yeah.
Which
So
means, so now I'm getting into the interpret, that the, what do we say? The number of times the baby cries and wakes the mother varies by about 1.0247 times from the expected number of times 2.1.
there you go. You got to bring that mean back if you're interpreting the standard deviation and just saying that's how much it will vary from that mean, whatever that mean is. In this case, it's 2.1.
Right.
Okay. So much easier to type, huh?
Yeah. I just was like, well, mm-mm. I
Mm,
refuse. I'm not writing. Donuts. Okay, at a bakery or at a certain bakery, the price of each donut is $1.50. Pricey donuts. Let the random variable D represent the number of donuts a typical customer purchases each day. The expected value and variance of the probability distribution of D are 2.6 donuts and 3.6 square donuts, respectively. Let the random variable P represent the price of the donuts that a typical customer purchases each day. What is the standard deviation in dollars of the probability distribution? Now, what I'm doing is I'm going to stretch you just a little bit, and we're going to talk a little bit more about this later on, but you have to think about your units. Really think about your units here, okay? So when I'm looking at my donuts situation, I'm told that the expected value is 2.6 donuts. And you might be tricked into thinking that you've been given standard deviation, but really you've been given donuts. And you've been given donuts, you've been given variance. And the reason you know it's variance is because of the units. Variance units will always be squared. So how do you go from variance to standard deviation?
got to take me a square root.
Gotta take you a square root.
And that would be, I don't know. I want to say 0.6, but I know that's not right.
While he's doing that, so we want to be careful here because it's asked us for, and this is the tricky part of this question, it's asking us for the standard deviation of P, okay? And right now we're determining the standard deviation of D. So he's putting X, but what he really means is D.
Oh, they call it D. I'm sorry.
And so let's go back and look at that. D represents the number of donuts. The number of
I like
donuts.
strawberry. I just don't
Ay,
like
ay,
square donuts.
ay. What does that mean?
I like strawberry donuts.
You like strawberry. Thanks, Mr. Robbie. Each donut is $1.50. Each donut is $1.50. Can I multiply? And the answer is yes. Yes. So at this point, I would say, okay, the standard deviation is 1.86 donuts, and I'm going to multiply to get that dollar or $1.50 times that to get the price. Okay, and we're going to talk. This is me kind of getting you ready for our next unit, which is if I want to change something, I've got to figure out what can I and what can't I change. When can I multiply and when can I not multiply? Okay, so this is like a prelude. Prelude? That's not the right word.
Preview.
Preview. Wow, tired tonight. A preview question leading us into. We're going to be talking about altering data sets and wanting to multiply or add something and change something. And we need to know when we can do that and when it's appropriate. Okay, so this would be an example of I need to change my standard deviation, and can I do that? Okay.
So this would be the standard deviation right here that you're looking for.
Yeah.
I ran out of room. I'm sorry.
Okay. Okay, so that's it. All you're going to be doing on your assignment here for Khan Academy is just a couple of them on mean and on standard deviation, and I hope it's super simple for you. Just remember, think about the formulas, think about the interpretations. Okay? Bye.